thrilled to be at Purdue again. It's been a while. And I just, before we begin, you know, we're a small group, so instead of putting questions in chat, please just unmute yourself and butt in. I'll be perfectly happy to just hear people's questions as we go, or comments. Okay.
Sorry to interrupt, just a comment. I wanted to remind you that this will be a two-part talk. We'll have a short break in the middle. So every first part would be around 40 to 45 minutes, and similarly for the second part, okay? Yeah.
Okay, so I just didn't hear that announcement. So is this my internet which is malfunctioning or yours, Manuel?
I am not sure, but I can repeat.
Well, no, I understood your comment,
okay.
But I just didn't hear it. It cut out. So I'm worried that my internet is failing.
You seem fine, so it might have been me.
Okay.
I hear you both perfectly.
You heard both of us? Okay, who knows?
Yeah.
Okay, perfect. Okay. Well, thank you again. And this is a second iteration of a talk that I gave in a seminar at MSRI in May on cubical sets. So I was just sitting there enjoying this wonderful series of seminars on cubical sets and closed model categories. And it suddenly hit me that it might be related to work I did several years ago on the construction of infinity-groupoids associated with L-infinity algebras. So at the time, it was a conjecture. I've tried to cobble together a proof, and I don't have enough time, I think, to present the proof, so I'll probably be fast-forwarding across all the slides I've written, but we'll see how it goes. So in the original version of the talk, it was about differential graded Lie algebras because I wanted it to be more accessible to the cubical set audience, which isn't really into homotopical algebra. I'm hoping that this audience is more sympathetic to L-infinity algebras. Can I have a virtual show of hands? Do you need more background on L-infinity algebras, or are people, you've all met them? You can do shows of hands in a room, but it's hard in Zoom. You can show your hands. There's a little flag. How does it go? Okay, thanks, Paul. Okay, well, that's one of you has met L-infinity. Okay, well, I know some of you know more than you're owning up to, but so an L-infinity algebra is a generalization of a differential graded Lie algebra, and for those of us who are into this kind of thing, it's actually more natural than a differential graded Lie algebra, but that's not necessarily the point of view I'm going to pursue here. So it's a cochain complex. I'll always work with cochain complexes in this talk. So my differential is all raised degree by 1. And so little delta's the differential, and it has a series of multilinear brackets for k greater than or equal to 2. So the first of these is a bilinear bracket, and you see that it's homogeneous of degree 0. The higher ones for k greater than 2 have negative degrees. And in fact, if you're being very fancy, you can think of the differential as the bracket with k equals 1. And the conditions on these brackets are graded antisymmetry in all the inputs. And then there's this somewhat intimidating generalized Jacobi rule. So I'm not going to go into the details, but I'll just suffice it to say that if all the higher brackets vanish for k greater than 2, this is exactly comes down to the definition of a differential graded Lie algebra. So let me just quickly run over what that is in case for those of you who haven't seen differential graded Lie algebras. So we're going to fix a field of characteristic 0. So just think of the real numbers or the rational numbers. And then we have our differential and a homogeneous bracket, which is skew symmetric, satisfies a graded form of Leibniz with the Kossel sign convention built in. and a graded form of the Jacobi rule. So in fact, differential graded Lie algebras have a long history in differential geometry, and then maybe a bit later in homotopy theory. So they're very well established. And L-infinity algebras were introduced as a kind of loosening of the theory of differential graded Lie algebras, and they're an extremely important tool in studying them. So we need to restrict attention to L-infinity algebras with some sort of nilpotence condition. This is because we're going to do algebra. And if we don't have this condition, then we're stuck doing formal algebra with power series. And I want to work with polynomial equations. So basically, it's analogous to the definition of a nilpotent Lie algebra. We're just supposing that there's a decreasing filtration on our complex such that it's compatible with the higher brackets. So what that means is if you take enough brackets, you eventually get 0. So, so in particular, there's one example which you can keep in mind, which is if all the brackets vanish. That certainly satisfies the Jacobi rule. And if all the brackets vanish, then we're left with a cochain complex. We just have the differential. So cochain complexes are sort of the extreme version of nilpotent L-infinity algebras. And if you like, you should try to think about what all the theorems we're going to say, all the theorems we're going to state, what they say in the special case of abelian L-infinity algebras. So our main object of study is the Murakatan equation. So this equation is an equation on elements of our L-infinity algebra of degree 1. And it's if you stopped the sum at k equals 2, you just have that the differential of x plus half of x bracket x is 0. Now, I'm sure all of you have seen that equation. That's the equation for a flat connection in differential geometry. So having its origin in that subject, then we generalize from flat connections on vector bundles to flat connections for a general principal bundle, which brings in Lie algebras. And then you can generalize that to differential graded Lie algebras. And then finally, there's the generalization all the way to L-infinity algebras. But note that this is a power series, this formula. And that will be not much use for us. So in order to make it into a polynomial equation, that's why we've assumed this condition of nilpotence. Now, you can, in fact, generalize from nilpotent L-infinity algebras to a more general setting where there's a complete decreasing filtration, but not necessarily finite. And that's the pro-nilpotent case. There's a further generalization where we allow something called curvature, which is a sort of 0 bracket. Now, in the case of curvature, we kind of assume that the differential no longer has square 0, but has a small curvature, which has positive nilpotence degree. Okay. Anyway, all of those things, for people who already know about this subject, you'll understand what I'm talking about. Everyone else can forget this. Anything that's written in red that is for the experts. Okay. So now I introduce a completely different subject, which is the Tom Sullivan differential forms, also known as Tom Whitney differential forms. So these are just differential forms with polynomial coefficients on the n simplex. Now, actually, you could take polynomial coefficients, or you could take analytic coefficients, or you could take C infinity coefficients, or CK coefficients. There are many different options. But in today's talk, we're going to take the algebraic route due to Sullivan, which is to take polynomial coefficients. So the n simplex is the geometric n simplex, which I'm sure you've all met, is the convex hull of the unit basis vectors in the Euclidean space, which is whose coordinates are spanned by the vertices of some abstract simplex. So if we take a simplex whose vertices are labeled 0 up to n, then we think about the Euclidean space whose coordinates are x0 up to xn, and then we take the unit vectors and take the convex hull. And that's equivalent to this set of coordinates, t0 up to tn. So these, now we take the polynomial coefficient differential forms, and this is the free differential graded commutative algebra generated by the coordinates t0 up to tn with the condition that their sum is 1. And then we take the differential of that condition and we get that the sum of the differentials dt0 up to dtn is 0. And then, so we take that. Maybe this is familiar to you. Now, the point is that if you take an L-infinity algebra and tensor it with a differential graded commutative algebra, any differential graded commutative algebra, you get an L-infinity algebra. In fact, if you take a differential graded commutative algebra and tensor it with an algebra over any operad, you get an algebra for that operad. So in our case, you see that the simplices form a cosimplicial space. And if we take the adjoint of that, then the differential forms on the simplices form a simplicial differential graded commutative algebra. Okay? So if I tensor that simplicial differential graded commutative algebra with L, then I get a differential graded let me try again. I get a simplicial L-infinity algebra. If L was nilpotent, the new guy is a simplicial nilpotent L-infinity algebra, okay? Incidentally, and I think this is quite cool, there's a notion in algebra of Reedy fibrancy, or actually I need Reedy cofibrancy. And this simplicial differential graded commutative algebra is Reedy cofibrant, which is in fact why we're using it. It's a Reedy cofibrant resolution of a point of the field, the discrete field. And as such, it's you know, in theory we could have taken any Reedy cofibrant resolution of F. All right. Now I can just hit my tensor, this simplicial L-infinity algebra with the Murakatan set. So that produces a simplicial set, which is commonly called the nerve of the L-infinity algebra. And I think for differential graded Lie algebras, this was introduced by Hinich, and unless somebody protests, I'm going to claim credit for it in the L-infinity case, although it's a rather obvious extension, so I don't get very much credit. Okay, nobody spoke up, so I think I will move on. Now, after Hinich introduced this, I think it was observed by various people. I don't have an exact reference where this first made it into print, that Sullivan had, so maybe I should give a quick recap on rational homotopy theory. So Quillen developed homotopical algebra in order to show that the theory of nilpotent rational homotopy types was equivalent to the theory of simply connected nilpotent differential graded Lie algebras. All right. And Sullivan rephrased that in terms of the associated differential graded commutative algebras. And the link between those two is given by the Chevalier-Eilenberg complex. If you have a Lie algebra, then Chevalier and Eilenberg associate to it the differential graded commutative algebra of Lie algebra cochains. That's just the exterior algebra generated by the linear dual of the Lie algebra. Well, it turns out that that has a generalization for differential graded Lie algebras, and in fact for L-infinity algebras. So we can apply this functor to L, to a differential graded Lie algebra. We get a differential graded commutative algebra, and Sullivan's functor applied to that differential graded commutative algebra is precisely Hinich's nerve applied to the original differential graded Lie algebra. So with this link, we see that actually Sullivan's theory can be recast in some ways more simply in terms of this Murakatan nerve. So we should think of this Murakatan nerve as the prime object of Quillen and Sullivan's theory, rational homotopy theory. Okay?
May I ask a question?
Yes, please.
Is there any finiteness assumption for this isomorphism?
I haven't taken any, oh yes, sorry. I was about to say I haven't taken any duals, but of course on that last line I took a dual. So I think perhaps there are finiteness assumptions for this identification. But the theorem itself doesn't have, I mean, if you're going to formulate things in terms of the Murakatan locus, in terms of the nerve, there are no finiteness assumptions. So I don't know, I haven't gone through comparing Quillen's and Sullivan's papers, but I expect then from your remarks. The thing is also that Quillen doesn't use differential graded commutative algebras, he uses differential graded co-commutative co-algebras.
Right.
So that's how he is also able to get around finiteness assumptions. Instead, he has these complete filtrations, and you know, he has the notion of connected co-algebras and all that. So he is very alert to finiteness assumptions, whereas Sullivan is more, I think, more concerned with developing a calculus. So Sullivan imposes finiteness assumptions without any concern.
Thank you.
I hope I'm not misrepresenting. But none of this is terribly important to my talk because Sullivan's point of view is not really relevant to anything that's going to, we can forget it. This was just for people who've read Sullivan's paper or any of the stuff that's come since. Okay, so here we have a sort of possible reformulation of Quillen and Sullivan's approach to rational homotopy theory. This is somehow close to what's in Basfield and Guggenheim, but I forgot to check what exactly statements Basfield and Guggenheim make. But I've formulated this very loosely, but there's a right-Quillen equivalence between nilpotent differential graded Lie algebras over the rational numbers and nilpotent simplicial sets with rational homotopy equivalences as their weak equivalences. And in particular, the Murakatan locus of a nilpotent differential graded Lie algebra is a Kahn complex. So that's a result which I proved in a paper a few years ago. So, you know, to prove results like this, we use Postnikov towers, basically. We need the nilpotents, and in some sense, the whole point of nilpotent Lie algebras and nilpotent things in general is that you reduce everything to the abelian case. So in the case of spaces, you reduce things to Eilenberg-MacLane spaces, and in the case of differential graded Lie algebras or L infinity algebras, you reduce things to abelian L infinity algebras, in other words, cochain complexes. And then the correspondence becomes the Eilenberg-MacLane space. And the correspondence becomes the Dold-Kahn correspondence. In fact, note, Eilenberg and MacLane can't state correspondences because they didn't yet know the notion of an adjoint functor. That's somehow the only thing that's missing from their work. And it's amazing that somewhere in the mid-50s, the idea of an adjoint functor was introduced for the first time and makes theorems like this possible. You can't state this theorem without knowing what an adjoint functor is. Okay, that was not planned, that remark, so it was incoherent. Okay, so this point I'm making here is too complicated. So let me just say in words what I'm trying to say here, that if you have an example of a fibrant simplicial set of a Kahn complex is the nerve of a group. And if you look at the nerve of a group, it has a very special property as far as simplicial sets are concerned. It's what's called two-skeletal. That is, one way of putting it, a loose way of putting it, is that it's completely determined by its two skeleton. So you don't need to know anything about the 3, 4, 5, and so on simplices of the nerve of a group in order to reconstruct the nerve. It's completely captured by the two skeleton. And in fact, we can, more generally, the nerve of a groupoid is captured by the two skeleton. The zero simplices, the vertices, are the objects. The one simplices are the morphisms. And the two simplices, if you like, are the multiplication table. That's the way I like to think of it. So, so this nerve is basically never two co-skeletal. And so I was interested in remedying that and producing a functor defined on differential graded Lie algebras, which in the special case that L was a Lie algebra, produced the nerve of the associated Lie group. And it had the nice effect, side effect, which that there's in the special case of differential graded Lie algebras in non-negative degrees, there's a groupoid which was associated to such a differential graded Lie algebra by Drinfeld. And you could take the nerve of that groupoid, and more generally, I would like a functor which produces that nerve. In other words, which reconstructs the Deligne groupoid. I'll come back to that point in the last slide of my talk. So what I was able to do was find inside this Hinich nerve a simplicial subset, which was the right one. And one of the main results of this talk is that I've noticed that there's a retraction from the Hinich nerve to this smaller nerve, which I don't know whether it's a terribly important result sort of in its own right, but it turned out to be crucial for proving the main theorem of the talk. Okay. So in order to introduce this, it's quite a long story to define this new functor, little gamma, and it takes us into the world of numerical analysis. So inside the complex of differential forms on the simplex, there's a subcomplex of a very special class of differential forms introduced by Whitney called the elementary differential forms. So they're given by this completely explicit formula. This isn't necessarily the easiest way to understand them, but well, since we're doing numerical analysis, we may as well just do it by explicit formula. So what can I tell you about this formula? The first thing to say is that there's one there's one of these basis vectors for each face of the simplex. And to a k-dimensional face, non-degenerate face of the simplex, we associate a k-form. The next thing to say is that this will be a basis over the rational numbers. Notice that the coefficients are at worst linear. And the story is very special in the bottom degree and the top degree. In the bottom degree, in degree 0, we have the k+1 vertices. And what you can see is that the elementary forms are just the span of the constants and the coordinate functions, okay? So that is indeed n+1 dimensional. In the top degree, so if k equals n, so if I0 up to ik are just 0 up to n, then this just equals, well, it's proportional to the volume, the standard translation invariant volume form, dt1 up to dtn, okay? So in that case, it's all differential forms with constant coefficients. So somehow in the intermediate degrees, it interpolates between linear coefficient differential forms in degree 0 and constant coefficient differential forms in degree in the top degree. And this is the beginning of a large development in modern numerical analysis, where you try complexes of differential forms on the simplex, interpolating between degree m+1 on the 0 forms and degree m on the top forms. Okay, so Whitney's result is that the complex spanned by the elementary differential forms is naturally isomorphic to the complex of normalized simplicial cochains on the n simplex. So we'll go over the case of if this is all a bit unfamiliar to you, we'll be going over the case of n equals 1 completely explicitly in a few slides. So hold on. So in the 70s, Dupont made an important addition to this theorem. He basically gave a completely natural proof of the Durham theorem for simplicial sets by constructing a simplicial homotopy for Whitney's projection from the differential forms to the elementary differential forms. I haven't given the explicit formula for Pn, the projection, but later I'll be giving the explicit formula for Dupont's homotopy. So in principle, you could reconstruct Whitney's formula. The key point is that if we're given a differential form, we know what its integral is on each face of the simplex, and there's a unique elementary differential form which has those integrals on the faces. So please.
I have a question.
Yes.
So you're considering this subcomplex as a cochain complex. You're not considering it as algebra with.
It's not an algebra.
Not an algebra, right? Exactly.
No. It's definitely not closed under product. It is, as it happens. This is a theorem that a student of mine proved a few years ago. It is a C-infinity algebra, it turns out.
Well, it's isomorphic to simplicial cochains, which we know has a...
That's right, but I don't know how to... I have no idea how to reconstruct the Whitney product, the cup product. That's an irony, isn't it? That we don't know how to write down in an elegant formula the Whitney cup product on the Whitney elementary differential forms. So don't think about the cup product in this talk. We're not interested in we're not interested in E-infinity algebras, if you like. We're just going to focus on in somehow rational homotopy theory, we erase, we just think of E-infinity algebras as commutative algebras, okay? That's the approach we're taking. But it was important that you asked that question. However, you asked, am I just thinking of C of delta n as a complex? No, I'm thinking of it as a simplicial complex, okay? That's crucial.
Okay.
All right, so there's this homotopy, and I don't think Dupont says this in as many words, but I assume that he obtained the formula for his homotopy by just thinking hard about Weij's proof of the Durham theorem, this famous proof that launched so many results in in spectral sequences and so on. So Weij reformulated the proof of the Durham theorem as an with explicit homotopies, as you can read in Bottom 2's textbook. And so I don't know, maybe you remember that in the proof of the Durham theorem, you need to use the Poincare lemma. And the Poincare lemma focuses on contracting around a point. Now, if I was to, let's do a little poll. Oh, if I was teaching at this point with Zoom, I'd be able to do an internet poll, but I don't know how to do that. So we're just going to have to speak up. So which point would I try to prove Durham's theorem? Suppose I needed to prove the Poincare lemma. For the n simplex, which point would I use to dilate around? Somebody speak up. Come on, be brave.
The barycenter.
Barycenter.
Well, that's it. Of course, you're going to pick the barycenter, and that will break the simplicial property. So, I'm sorry, I've got a, do you mind? I'm going to clear my throat. It didn't work. Sorry about that. So that's going to break the simplicial property. So that won't work. So the next step you might think is, oh, well, maybe we should use one of the vertices. And that actually is compatible with all the simplicial maps which don't involve that vertex. So that's an improvement. It's something a bit counterintuitive, isn't it, to do the Poincaré lemma around a vertex of a convex set, but it's perfectly legitimate. When we say that a set is star-like, that's not including that we're using a center which is on the boundary. So that's, I think, Dupont's main new idea. Now, the problem is that Simplex has n+1 vertices. So which one are we going to use? So the natural idea would be to take the, let's take the average somehow. Let's maybe take the barycentric combination of these Poincaré homotopies, but that doesn't work either. So the formula that Dupont cooked up is somewhat more complicated, but it does use the Poincaré lemma for each vertex of the simplex. So, so my formula for this sub-functor is to introduce this idea that if you have a homotopy, you can take on a differential graded Lie algebra, or more generally an L-infinity algebra, you can take the kernel, or you can take those Murakatan elements. I'm sorry, I'm going to get up and get my pen because I forgot to get it. So now that I've got my pen, I can point. So can you see my cursor?
Yes.
Yeah. Yeah. So suppose I have a Murakatan element, then I can just look at just those Murakatan elements that satisfy a gauge condition, by which I mean I've got a homotopy and I ask that the homotopy kills the Murakatan element. And so I introduced the following notation, the Murakatan locus of an L-infinity algebra satisfying a gauge condition, that is, on which a homotopy vanishes. And that's it. This is still clearly a simplicial set, and this gives a functor from nilpotent L-infinity algebras to simplicial sets. That's because the functor, the nerve, is simplicial, and the homotopy is also simplicial. Okay? Now, so you then prove, the main thing you have to prove is actually that this takes fibrations and trivial fibrations of nilpotent L-infinity algebras. Fibrations, for me, are just surjective maps. And trivial fibrations are surjective maps, which are quasi-isomorphisms, and that it takes them to Kahn fibrations and trivial fibrations of simplicial sets. And the proof of that result is by induction on the filtration of the nilpotent L-infinity algebra. So you basically, the idea is to prove results for the abelian case and then prove the fibrancy and then extend the result by, well, anyway. So to prove fibrancy, to prove the existence of horn fillers, I use the contracting mapping principle. So that's the main place I use nilpotence. Nilpotence can be viewed as saying that I have actually a Banach algebra and a contracting map. And in this way, what I'd like to remark is that, after all, the theory of Lie groups is a branch of the theory of ordinary differential equations. Lie was studying ordinary differential equations when he came to the theory of Lie algebras. And as we know, the existence theorem for solutions of ordinary differential equations is proved by the contracting mapping principle. So in some sense, this theorem generalizes the arguments of Lie, which were ordinary differential equations, which is the contracting mapping principle on the one simplex. It generalizes it to some sort of equation on the higher simplices. And if you look through what's going on and what Dupont's homotopy actually tells you, what you see is that in some sense, the one simplex case of this result is reproducing what it is that Lie was doing when he said that an ODE has a solution, and then used that to define the exponential map for a Lie algebra. Okay, anyway, that's a side remark.
I'm sorry, Ezra, could you say again what S-Lord bullet was?
I haven't defined it yet. All I'm told you is that it's a homotopy for the projection from the differential forms to the subcomplex of elementary forms. But I'll give you an explicit formula in a moment.
Okay.
Is that okay?
Yes, absolutely. Thank you.
Okay, and I'm running out of time, but in fact, I'm going really slowly. Well, I mean, I need several hours, I guess. But anyway, it's worth remarking that if the L infinity algebra vanishes in degrees minus k and below, then this simplicial set is k truncated in the sense of Duskin. That is, it's what we would now call a k groupoid. And in particular, if k is 1, then we get a groupoid, the nerve of a groupoid. And as I'll remark at the end, if I have time, if k is 2, we get, which does occur in differential geometry, for example, in Poisson geometry, then we get a 2 groupoid. Notice this gauge condition, I think of it as, I call it a gauge condition because it's just like the condition in Maxwell's theory of electromagnetism. The Lorentz condition that we take the divergence of a connection to be 0 is an example of this gauge condition that I'm giving you, okay? So, right. It's worth, I'll run over this very quickly, that in the special case that L is abelian, we get the Eilenberg-MacLane space. There's a shift in degree of 1, but apart from that, this is essentially reproducing the original definition of Eilenberg and MacLane, although it's restricted to vector spaces. Their original work, they define for any chain complex of abelian groups a simplicial abelian group, but this is only for vector spaces. In the special case that we start with the nilpotent Lie algebra, we get the nerve of the associated Lie group. And so in some sense, this construction generalizes the Baker-Campbell-Hausdorff formula. Okay, so now I should, before the break, I meant to break now. Can I quickly do this? Because otherwise I'm too far behind? Or,
yes, go ahead.
Yeah. So actually, I already said a lot of this. We have the Poincaré homotopy around each vertex, and I'll send the slides out in a minute, and so you'll have the formulas. So we basically use the Poincaré homotopy around each vertex, and then Dupont's homotopy, to answer Mahmoud's question, it's given by this rather alarming formula. But it's quite elegant, I will say. This homotopy has far more properties than you might guess based on its just giving the formula. It turns out that in later in my talk, I'll need homological perturbation theory. And for that, we need something called the side conditions. And it turns out that this homotopy actually satisfies the side conditions. So I'm going to skip these remarks, but let me just focus on the last remark, which is that notice that this homotopy is equivariant under the permutation group acting on the vertices of the simplex. So this is there's something rather bizarre in topology that while we work with simplicial sets, there are certain situations where we actually get symmetric sets. And one of them is when we take the nerve of a groupoid. That is, we have an action of the symmetric group on the simplices. And the whole thing is equivariant in a certain sense. So in particular, and I want to focus on this special case, if n is 1, then we have the one simplex, and then the symmetric group action is just reversing the direction of the one simplex. And so I'm going to, in a second, use that the Dupont's homotopy is equivariant under the action of the reversal map. Okay, the reversal map is the exchange for the beginning and end of the one simplex. And just, I think, yeah, let me do these two slides if it's okay, and then I'll break. And then I'll cough. So here's the explicit formula for the Dupont homotopy in the case of the one simplex. And this is actually the only case I need in my talk today. So, so what is this doing? It's your favorite homotopy. If you were trying to think of what a, well, maybe not your absolute favorite, what I need is a homotopy that if it takes the value, sorry, oh gosh. So we're on a one simplex. What's it going to do on the one forms? It just takes the average. It has to produce a, sorry, what am I saying? Let me try again. It's got to take a one form to a function. That's what I should be saying. It's reducing degree by 1. So we're looking for something which starts with a one form and produces a function. And the homotopy will, when we apply S to a one form, we're going to get something which vanishes at the endpoints and whose derivative is the one form we started with minus its average. So if you have a one form, you can subtract out of it the constant one form, which has the same integral. And what all we do is integrate that differential form to get Dupont's homotopy. So Dupont's homotopy is the only one you would invent for n equals 1, and it's only for n greater than 1 that it gets much more complicated. So I've made completely explicit on this slide what the flat the solutions of the Murakatan equation that satisfy Dupont's gauge are, except that there is no Murakatan equation in one dimension because, or very little Murakatan equation because the two forms vanish. So it comes down to actually what it says is that we have solution of a connect. So we integrate a connection, and we have a in such a way that the connection is actually a constant connection up to a gauge condition. So I'm sorry, that was all a bit jumbled, but yeah, let me just skip that then. I think I'm jumbling it too much. So let's take a break. I'm sorry.
Okay, we can take a 5-minute break, I guess. Yeah.
Okay. Any questions?
Ezra, the differential graded algebras here can be positively graded, negatively graded, mix, everything.
Well, it's up to the condition that we have nilpotence. Yeah, it's completely, yeah, there's no further condition. The only condition I mentioned was the nilpotence. Yeah.
Okay.
So for example, yeah, so you're wondering, suppose I take the abelian case. I think it's always best to start with the abelian case. So you were asking, do I have any conditions on my cochain complexes? And the answer is no. They're unbounded above and below. But when I apply my functor, I throw away the positive part. Completely. Yeah, it doesn't pay attention to anything above degree 1.
Yeah.
Well, sorry, above degree 2, I should say. It needs what's going on in degree 2 to be able to test the Murakatan condition in degree 1.
Yes.
Okay.
So it still addresses like differential geometry where you have differential forms with values in Lie algebras. That's just like at the cutting. That's like the boundary of where it's.
That's right. But but we can pay attention to the higher degree part by going to derived geometry. So it turns out that this little gamma is the classical locus of a derived stack.
I see. So
and that's the best way to think of it.
With negatively graded CDGAs, and that brings
in that way you handle the complete unbounded in both directions.
Okay.
Provided you have nilpotence.
Okay.
Or pro-nilpotence. So let me remark there that if in the case of an unbounded abelian L-infinity algebra, in other words, a cochain complex, then we recover this derived stack statement is essentially
the spectrum.
It's the statement in Illuzi's thesis that cochain complexes correspond to simplicial, co-simplicial abelian groups. That's one way of thinking of it. That's what an abelian derived stack is. It's a, I don't know, fortunately there's nobody here who's going to attack me for that statement. But an abelian derived stack is nothing more nor less than a simplicial, co-simplicial group. Abelian
That's
group.
like a, is it like a spectrum?
No. No, this co-simplicial aspect is completely different, I think. The idea of co-simplicial is that it's a generalization of the idea of, it's a non-linear analog of, so if you have a coherent sheaf, you can look at syzygies.
Yeah.
And the idea of derived schemes is a non-linear analog of syzygies.
Okay.
And then derived stacks is putting that all together in a simplicial framework. So there are several different ways of understanding. So let me touch base, make contact with what you were asking. There are several different languages for derived schemes. You can work with differential graded. So the spectrum of a derived scheme can be taken in different categories. You could look at differential graded commutative algebras. You can look at simplicial commutative algebras, or you can look at spectral commutative. You can look at E-infinity, connective E-infinity spectra.
Yeah.
So ring spectra. So I think that's maybe what you had in mind. So if you think of a derived scheme, God forbid, as a connective E-infinity ring spectrum, then there's a theory of derived stacks in that context. And Lord knows there are bigger experts on that here than me.
Thank you.
So we're at, I've lost, oh, there we are. I lost the gallery. I just have one last, because none of us are broadcasting. Well, you are, Mahmoud, but it's of no use because you need to, if you're going to have your video on, you should put a light on your table you need to highlight. That's better. You need to highlight your face. Yeah.
I have a question if I can.
Please.
You're mentioning the story about symmetric sets. Have you seen anything written in that direction?
So the problem is that the literature is so big, and my brain, as I get older, gets smaller and smaller.
Me too. Yeah, me too.
And so, yes, I think the answer is yes. But, you know, at this point in my life, I only remember things if I think I'm going to use them. And so there is definitely something written about it. Look, I mean, apart from anything else, if you Google any question like this, you immediately hit the, what's it called? The N stack or something, that, you know, that blog. And it's like a strong attractor for Google questions about homotopy theory. It can be annoying because there's a lot of mistakes in that blog, unfortunately. And I think that's where a lot of grad students are learning this stuff from. But no, that's a really good question. But the interesting thing is that I think it's not emphasized because as soon as you move to the nerve of categories, you have to give that up. That's exactly what you give up. So, okay, to answer your question, it's in some sense the difference between delta sets and gamma sets.
Yeah, exactly. Yeah.
Yeah. So perhaps, you know, looking into Siegel's work and work that follows that, you can find. So it's somehow the difference between symmetric monoidal functors, because I think you probably know that a Siegel space is exactly the same thing as a co-lax symmetric monoidal functor.
But you see, what I had in mind is more if I'm looking at papers of Lawrence or maybe Bush, Murillo, etc. They're often looking for symmetric formulas for models in rational homotopy theory. So I was more looking for, say, the analog of your paper, but written with symmetric sets and not simplicial sets.
Well, I could have just written it with symmetric sets, you see. Okay. I think, so the only question becomes, is there a closed model structure? Now, actually, I didn't write my paper using closed model structures.
No, exactly.
But I could have. But I could have, obviously. I mean, I proved all the results needed to, I mean, I checked. The point of my paper is I checked that I have a adjoint pair, which takes fibrant to fibrant and trivial fibrant to trivial fibrant. That's what I did.
You have no adjunction in your paper. You just have
that's
gamma.
Probably true. But it's like the way I write the functor, it's obvious it's an adjoint functor, you see. That's all.
Okay.
Yeah.
And another question.
Hang on. But I just want to finish. The point is, what I didn't establish is what is the closed model structure on symmetric sets.
Yeah.
My functor goes to symmetric sets. But once you have established that the Quillen closed model structure also gives a closed model structure on symmetric sets, and I don't know off the top of my head if that's true or not, but I suppose it is. The reason I suppose it's true is that all the standard functors that construct, I think, all the standard, somebody correct me, all the standard functors that construct subdivisions actually take symmetric sets to symmetric sets. So that when you, I mean, sorry, let me try again. The real problem to prove you have you need to construct a fibrant resolution. And if your fibrant resolution functor happens to preserve symmetric sets, then there's nothing more to show. Then you know that you have a closed model structure, and then you can simply verify that any proof that there's a right Quillen equivalence of categories will go over to that the target is actually symmetric sets and not just
Okay, and if I can, one more question. You're saying functor, but gamma is a functor from which category? The nerve, the nerves eats infinity morphisms. But
so it's actually a functor on a much bigger category. It's a functor on, I need some condition so that the Murakatan equation holds. So if I take the category of those L infinity, somehow those L infinity algebras that have enough finiteness that the Murakatan equation is meaningful.
But my point is about strict morphisms with respect to infinity morphisms. The nerve is
strict.
Yes. Have you seen anything? Because the nerve is definitely from
There's no extension to Schmaps.
Alors, okay.
Yeah.
There is one intermediate guy. We can talk about that.
Okay. Can you stick around for a few minutes after the talk?
I don't think so, but let's see. But maybe
we'll set a time. We'll fix a time.
Yeah,
okay.
exactly.
Brilliant.
Sorry.
So I will in fact need the distinction between different kinds of maps at the end of my talk. Okay, we're ready to.
Yep.
Sorry. Where am I? I can't find full screen. Oh, there we are. Great. So now the subject of the talk. which is cubicle nerves. So this is the new topic in this talk. Everything I've talked about until now is contained in my paper in Annals from, I can't remember, 2009 or something. So what I'm going to do is define a different nerve, an analog of little gamma, and an analog of the Hinich nerve also in the cubical setting. And the advantage is going to be that differential forms on cubes are easier to understand than differential forms on simplices. The Durham Theorem, you may well, when you learned the proof of the Durham Theorem, have learned it for cubical sets and not for simplicial sets, because the proof for cubical sets is much easier. I know that when I was a grad student, Bott proved it for cubical sets effectively. And I was, in some sense, really angry. I sort of, I was this excessively young grad student and got annoyed that he hadn't proved it for simplicial sets. But now, of course, I understand better that he was onto something. So let's quickly run over I spent the first 58 years of my life hating cubical sets. So somehow the purpose of this talk is to make me love cubical sets. So first, the cube. So the cube is the one simplex raised to the nth power. And we have, for each coordinate, there are n coordinates, directions, 1 up to n. And for each of those, we have a coface map. There's a top coface and a bottom coface, all right? And those are indexed by 0 and 1, and they're just given by specializing the coordinate to 0 and 1. And we also have codegeneracies, 1 in each coordinate, so there are n codegeneracies. Notice that's the same number as there are for simplices, whereas there are far more coface maps. And that's just given by forgetting a coordinate. And now there are new maps, which we don't have the analog of in the simplicial setting. So the first of these is the lower co-connections. The reason I call them co-connections is because they're adjoint to what we will really be interested in, which are the connections. So notice that if I have 2 consecutive coordinates, I can multiply them. So in that case, if either of them was 0, we get 0. We get a vertex. So they map on the square, they map 2 sides of the square to the initial vertex. Then they retract everything else to the 1 simplex, and they leave the vertex 1, 1 at the top vertex. So what they are is a retraction of the square to its diagonal. And what was discovered by Brown and Higman was that the theory of cubical sets was somehow defective if you left these morphisms out of your category of cubes. And so any good theory of cubical sets has to have these maps built into them. Now, some of you will complain that I'm using the product and not the minimum function, which is the more usual one and the one that was mentioned in Brown and Higgins's work. So the thing is that there's an obvious defect to the function minimum, which is that it's piecewise polynomial, but it's not actually polynomial. Whereas this map it's in fact not just polynomial, but quadratic, and in fact bilinear. And that's going to actually be essential for me in my talk. So as far as I can work out, it makes nowhere in the theory is the replacement of the minimum function by the product function of any importance. But it's essential to me now in this talk that I take this version. We also have, if you conjugate the lower co-connection by the reversal map in all the coordinates, you get the upper co-connections, which retract if you take the square, it retracts 2 of the faces to the top vertex and leaves the bottom vertex where it is. And it's given by this explicit formula. And there's finally the reversals, which exchange the top and bottom vertices in one direction. So they exchange the top and bottom faces in that direction. So actually, it's very interesting. Boardman and Vogt, in their book on operads, so they introduced this functor W that I think many of you are familiar with. And clearly, their functor is very naturally wanting to sit in the cubical world because it involves taking a union of cubes parameterized by trees with certain identifications on faces. And then also they need these co-connections, except they have the option of using x, y, or the minimum of x and y. And in fact, they mention both choices in their book. So, so it turns out you could say that one of the fundamental theorems of the theory of simplicial sets is that simplicial groups are fibrant. And it turns out that that isn't true if you leave out the upper or lower co-connections or connections from the theory. So this was studied in Tonks's thesis, which I only learned about while preparing this talk, but it's really one of the most fundamental papers in the subject of cubical sets. Oh yeah, I remarked that the only reason I'm using lower connections in this talk is because the function xy takes less space to write than x plus y minus xy. But obviously the theory is isomorphic under exchange of lower and upper connections. You can actually use both at the same time, and it's the theory will go through. There's no need to use both lower and upper connections. You have to use at least one of those two, but there's no defect to using both. And if you use both, then you're allowed to also put reversals into the category. So that's the maximum category that I'm going to be able to work with, the one with faces, degeneracies, lower and upper connections, and reversals. So now I introduce the differential graded commutative algebra of polynomial coefficient differential forms. So this is very easy to define. We just take the polynomial ring in the coordinates x1 up to xn and their differentials. So it's just the tensor power of the differential forms on the one simplex, and certainly it's contractible. So all of these things are so much easier to see when we are working with cubes than with simplices. And you'll see that this continues, that the proof of the Durham theorem, for example, is just one line for cubical sets and considerably more complicated for, as we saw, for simplicial sets. Maybe I should have emphasized, for me, the Durham theorem is the statement that the Whitney forms on a simplicial set is quasi-isomorphic to all the polynomial coefficient differential forms. That's what I meant by the Durham theorem. So the Durham theorem now for cubical sets will be, we'll have a notion of elementary forms, which I'm now introducing. It's just the tensor power of the elementary forms on the one simplex. So on the one simplex, the elementary forms are just spanned by 1, x and dx. And so now we take the tensor power of that complex together to get the elementary forms on the n simplex. And we have a projection from the differential forms to the elementary forms on the n simplex. And we have a homotopy. And this homotopy is so much simpler to write down than Dupont's homotopy. Notice that it is not equivariant with respect to the symmetries on the coordinates. So this absolutely breaks symmetry. Remember that in the case of Dupont's homotopy, it was equivariant with respect to symmetries. And I don't think that if I symmetrize this homotopy, that the theory goes through. But to be honest, I realized last night that I'm not certain of that. So if somebody wants to look into that, it's possible to symmetrize this homotopy, and conceivably that symmetrization continues to be compatible with the space and degeneracy and connection maps, but I doubt it.
So Ezra,
Okay.
quick
Yes,
if you triangulate your cubes,
yes.
how is this compatible with Dupont?
I don't know what you mean by compatible. I mean, there's a zigzag, but I'm not going to say any more than that.
Okay.
I mean, in the world of quasi-isomorphisms, by which I mean some sort of zigzag, sure. But, I mean, there's no direct relationship.
Yeah, okay.
You know, these are two disparate formalisms. But if you want to know more about the relationship between differential forms on cubical and simplicial sets, the best place to look, I think, is the literature on the finite element method, because that's something that people are interested in. Okay? Because that's what the finite element method is. You take a simplicial or a cubical set and you look at piecewise polynomial differential forms on that. Okay, so this is the new result of this talk. That these homotopies are compatible with all the cubical operations. So it's essentially the reason I'm giving this talk is I noticed that this formula is compatible with the connections. So that's the main take-home message, that, that now I can imitate step by step the construction of my functor gamma, and it will land in the category of cubical sets with connections. That's the key point. So so let's run over that construction.
And
If
Ezra,
I
by connections, you mean lower, upper, and reversal?
in fact, yes, yeah, but you only need one of the sets of connections for the theory to go through. But yeah, it's actually compatible with all of them. Yeah.
Okay.
Yeah. So so if I have a cubical set, I can form the differential graded algebra of differential forms on that cubical set by taking this coend. So you know, essentially all I'm doing is for each cube, I take a copy of the differential forms, and then I take the co-limit over all the morphisms in the cubical category. And this homotopy descends to a homotopy on that differential graded algebra. It's not compatible with the product, but on the complex, and gives a homotopy to the projection onto the complex of cubical cochains. All right? And
sorry,
yes.
a quick question. I think I did not get why you need the connections.
Somehow it doesn't capture homotopy theory. Whereas simplicial sets, if you like the following theorem, that there's a Quillen equivalence between simplicial sets and spaces. So that isn't true for cubical sets without connections. And not only is it not true, it's already not true for the Eilenberg-MacLane spaces. So, you know, there's a Quillen equivalence between the category of simplicial abelian groups and the category of, if you like, Eilenberg-MacLane, of spaces with the homotopy type of an Eilenberg-MacLane space. Okay. And that fails for cubical sets, okay?
But technically you could define this S, cubical S, without using the connections? You
could, but it puts you in the wrong category.
Okay.
Yeah. It doesn't capture homotopy theory. That's the discovery of Tonks. Yeah.
Is this like technically to make it into a strict test category or something?
Oh, I think that's correct, but I don't know. Yeah, I think yeah, if you're into homotopy type theory, then this exactly. But I'm not. I don't know what a type is. So it turns out that we all do type theory without knowing it, but yeah, I'd prefer not to go there. Okay. So I just imitate my definitions. I define the Hinich nerve, but with the cubical differential forms. That produces a cubical set, and now I can put this very simple gauge condition. And so this replacement for the functor I defined earlier is somehow much more approachable. I hope you believe me. somehow, because this homotopy is so much easier to understand. And so now I'm going to explain a relationship, but the rest of my talk is to relate this new functor to the original functor gamma L. So the surprising result is going to be that it's naturally isomorphic. Okay? And that's going to be an application of this somewhat intimidating but very explicit subject called straightening and unstraightening. So in some sense, the theory of straightening and unstraightening is a bridge between homotopy theory done simplicially and homotopy theory done cubically. And as you know, whenever you want to relate homotopy theory in two different settings, I think, Mahmoud, in your language, it would be, if you want to relate, if you like, homotopy theory in two different test categories, the best way to do it is to take something which is a kernel between those. So I'm going to give you a co-cubical simplicial set, and that will bridge the two worlds of simplicial and cubical. And that co-cubical simplicial set is called capital Q. And it is the subject of the theory of straightening and unstraightening. So this whole subject has a very lengthy, I'm sorry, I said it exactly the wrong way around, didn't I? It's a co-simplicial cubical set. That's what I should have said. So this object is not necessarily familiar to all of us, but it's really not a very difficult thing to introduce. So it goes back, I think implicitly, certainly, in the work of Boardman and Vogt. It is written about at great length in the chapter of Lurie on straightening and unstraightening. The key result there is that it's contractible. And the easy way to prove it's contractible is to geometrically realize it and see that you have something that's convex. In some sense, that is the content of straightening unstraightening. So what is this cubical set Qn? As a cubical set, in the sense of cubical sets with connection, it was actually introduced by Kapulkin, Lindsay, and Wang. The people who work in homotopy type theory are interested in using cubical sets in order to formulate homotopy type theory. So that's led to a renaissance of interest in the approach to homotopy theory using cubical sets. So what you do, so let me start with the square. If I take a square, then I can take one of its faces and contract it to a vertex. And I'm left with a two simplex. And that's all that these objects are. This here is a picture of Q2. And this process is how Q2 is constructed from the two cube. So the two cube, the square, I've contracted one of its faces, and that's produced something which looks awfully similar to the two simplex. And it's explained by Lurie that this co-simplicial object, you should not confuse it with the simplex. It has the same face maps, but different degeneracies, which is same co-face maps, but different codegeneracies. But anyway, whatever it is, it's given rigorously by a straightforward procedure in which you put an equivalence relation that if any of the coordinates are equal to 0 in the cube, then you identify that face with the corresponding codimension 1 face. So you, as soon as one of the coordinates is 0, you don't care what the previous coordinates were. They may as well have been 0. And after you perform all those equivalences, you're left with Qn. So one way of saying it is that the lower ith face is collapsed to a face of codimension I. Okay, so that produces something whose geometric realization as a cubical set is homeomorphic to the n simplex, and in particular, it's contractible. So in that way, I think we produce a reedy, what's the language? We've just produced a reedy cofibrant cubical set. Sorry, okay, I'm going to get it wrong, so let me pass. So there's a easy way to understand this by constructing a polynomial map from the geometric realization of the n cube to the geometric realization of the n simplex. It's given by this explicit formula. I think this formula is pretty well known. And while I was preparing the talk, I found this mnemonic for the formula that the coordinates on the n simplex are given by this amusing equation. So I think another way of thinking about all of this is that there's a tropical aspect to this subject, that on the simplicial side, we're using addition, and that somehow gets replaced on the cubical side by multiplication. That's, roughly speaking, what straightening unstraightening seems to be about, a sort of tropical approach to simplicial sets. Let me move along. I'm going to just pass on this. And so what that shows now is that we can, so if you take the cubical set Qn, you can take all maps from Qn to your favorite cubical set. And by maps, I mean they have to preserve the connections, okay? And if you have reversals and upper connections, you can preserve those too. And that produces now a set, and as n varies, I get a simplicial set. And that process of taking a cubical set and producing from it a simplicial set, that's actually a Quillen equivalence. And I'm going to, that's the subject of my talk, that resulting simplicial set. So a more direct way of thinking about it is at the bottom here. I take those Murakatan elements in the L infinity algebra of differential forms on the Q simplex, on the Q, oh, sorry, on Q. So take Qn, that's some cubical set. Take its cubical differential forms. Tensor with L, that's a L infinity algebra. Take its Murakatan locus on which our favorite homotopy vanishes. And that's a set, and they assemble into a simplicial set. So it's a little confusing, but this unstraightening is now again a simplicial set. There's I left out L here. Okay. And let me skip that. So the theorem, which I don't have time to finish the proof of, unfortunately, of today's talk, is that actually there's a natural isomorphism between this new construction and the old one. So in some sense, I've given, in my view, a much more approachable way of producing this functor gamma of L. Somehow, the functor gamma of L is the right functor because it has been tested to give the right answer in so many different cases. The abelian case, Lie algebras, differential graded Lie algebras, which vanish below degree 0. And so this new construction is somehow much more elementary. And I think this result is quite powerful. So
and you mean isomorphism, not weak equivalence.
I mean isomorphism, absolutely. Yeah, it's, I certainly, from what I've said, you already know that it's a natural equivalence, a natural quasi-isomorphism, because I've already given you a zigzag. And I've shown, somehow the proof that gamma was equivalent to MC also shows that gamma Q is equivalent to the geometric realization of MC cubical. And somehow putting it all together, I think you can show that they're all equivalent. But I'm going to show they're actually isomorphic. Okay? So to prove that, I need homological perturbation theory. And I need some results that I actually didn't know in homological perturbation theory, but I found in the book of Ledet and Valette. And I'm also going to refer to some calculations in a paper of Berglund, which gives some slightly more explicit approach in the case of, in the L infinity case.
Ezra, I don't know if this is a good time to ask her. Maybe you're going to talk about it, in which case I'll wait.
Yeah.
The homotopy groups of this space, they are related to the Chauvel-Eilenberg cohomology groups of the...
Well, so the point is that it's K-connected. So suppose L vanishes. So suppose Li equals 0 if I is less than or equal to K. That implies that pi I of gamma L equals 0 if I is greater than K.
Mm-hmm.
So that's not the answer to your question, but I think you should bear this in mind before you ask your question.
No, I know that they are not equal unless there's some...
No, but I don't know what you mean by equal. The point is, so which homotopy groups are you interested in? So pi naught, each homotopy group is somehow important in deformation theory. Pi naught is the coarse moduli space of L. L, right. Remember, L is an L infinity algebra, so it governs a deformation theory.
Right.
And pi naught is the gauge equivalence classes of Murakatan elements. And that's the coarse moduli space.
Yeah.
So that's well known. Pi 1 at a Murakatan element is the isotropy group. So it expresses the extent to which we have a stack and not a fine moduli space. Pi 2, well, I wrote a paper on that. In the case of Poisson manifolds, you can take the Schouten algebra of multivectors, and in that case, pi naught is the Poisson manifolds, the equivalence classes of Poisson manifolds. Pi 1 is the outer Poisson. So all the Hamiltonian morphisms modulo the inner ones, the ones generated by a Hamiltonian. And pi 2 is the Casimirs. Mm-hmm. So each homotopy group in any given deformation situation has a very natural meaning in terms of mathematics.
Yeah.
Okay.
Can I say something?
Please.
Excuse me. There is a short answer to Mahmoud's question. There is a beautiful theorem by Berglund. If you want to compute pi n of the gamma functor, the complex at point alpha, which is a Moror-Cartan element, it's very easy to compute. You take your Moror-Cartan element, you twist the infinity algebra by alpha, and you take the n minus 1 or n plus 1 homology group of this twisted L infinity algebra.
But I think his theorem has some connectedness assumptions.
No. You look at pi n at point alpha. Sorry.
He has nilpotence assumptions because I think nilpotence is what's...
nilpotent, well, complete assumption. He has a complete filtration, blah, blah, blah.
Because if you don't have some completeness, then you don't have homological perturbation theory.
Yeah.
Okay, and which is the subject of my remaining... I've run out of time, but just to summarize what I'm about to do, if I completely run out of time, it turns out that we'll be able to construct a map using homological perturbation theory from gamma of L to the new Q, the unstraightened gamma Q of L. So we get a natural transformation of functors, and then you can check that it, in the abelian case, it's an isomorphism. That's just Eilenberg-MacLane spaces. So, and that's the end of the story. So that proves that the two functors are isomorphic. So, so the problem is to construct such a map. And to do that, I needed the fact that there's a backwards map in homological perturbation theory between the Murakatan sets of an L infinity algebra and of its if I have a contraction of it. So this, I was going to skip, I mean, I put this in the slides, but in fact I want to skip it. But let me run over it like super fast, just to cover the main points. So there's the standard notion in homological perturbation theory of a contraction where we have a complex V and a subcomplex W, and F projects from V to W, and G is the inclusion, and H is the homotopy. And then if you have a Murakatan element in the endomorphisms of V, so you have a new differential on V, you can deform the whole contraction. So this goes back to the early 60s, it turns out. And these formulas are extremely beautiful. The nilpotence that I was just referring to is, so that's, we need enough nilpotence that these formulas converge. Okay, so if you haven't seen these formulas before, you're not going to understand them now. But what I want to do is apply this now with something called the tensor trick to the Chevalier-Eilenberg complex of the L infinity algebra L. So this is a generalization of the Lie algebra chains of a Lie algebra for any L infinity algebra. I'm not sure, it's probably due to Stashev. Bruno, do you know if that's, probably due to Stashev.
Oh, I don't remember.
Yeah.
Stashev, I don't.
Yeah,
I
mean, it was observed in the late 80s that you can reformulate being an L infinity algebra as having a codifferential on this coalgebra. So
maybe it was the original definition.
Oh, that could be. Yeah. So so it's basically the exterior algebra of the complex L. And in the Kossel world, it's the bar construction. So so a L infinity structure is precisely a Murakatan element on this guy. You know, the differential of L gives a codifferential on this bar construction, and then the L infinite structure is captured by a Murakatan element. And so we're going to put this into homological perturbation theory. So to do that, I called it the tensor trick of Hubschmann, but I realized a second ago that it's actually Guggenheim, I think, or it goes back to the 70s, the tensor trick. So, or maybe even the 60s. So we extend our contraction to this cobar construction, this bar construction, by tensoring up. And the very difficult, the difficult part of the subject is that if you just took the naive formula for H, remember that we had the formula for the homotopy on the cube. And this is analogous, but this isn't symmetric. So it doesn't actually descend to the bar construction, to the Chevalier-Eilenberg complex. So you have to symmetrize it, and you get this enormously complicated formula where on some of the factors you get the projection, and on some you don't, and on one of them you get H. And then there are some coefficients. So I took this from Beglund's paper, but actually the explicit formula is not important. All that's important is that it's the symmetrization of this homotopy. Okay, so so you just run the formulas you run these formulas now, and you get a deformed contraction in this setting on the Chevalier-Eilenbergs. And so it turns out that F mu, the deformation, the deformed projection, is a morphism of DG coalgebras. It satisfies this equation, and that's going to be all I need to construct the map from gamma L to gamma QL. Okay, so I think the analogous calculation was performed by Markov. So here I spent a week and a half writing these 3 slides. So I'll page through them, but I won't have time to tell you about them. But you can, there's this super elegant proof, which just takes essentially a few lines that proves this basic formula. And so what does it rely on? Maybe I should say the key things it relies on are these three explicit formulas. So this, I think, I will credit this to Berglund, that he isolated these three equations. And checking these equations is actually, well, the first two are relatively easy. The third one, you need to just make sure, you have to keep track of. So it takes about half a page to check that formula. But that's the key formula that everything else relies on. So what our problem is that H itself is not a coderivation because we've symmetrized. And we're somehow using enough remnant of H want to be a coderivation that we're able to push the formula through. So, and this is the proof. It's that's the whole thing. So I'll move on. But it's, as you see, it's not very much work now once we've set everything up. So as a corollary of that, you see that that actually M is an L infinity algebra. So that's, in other words, D sub mu is a coderivation. It has square 0. So by definition, it's an L infinite structure on M. So actually something which maybe Bruno can explain to me at some time is G mu is also a morphism of DG commutative coalgebras. And somehow in both Lode and Valette and in Berglund, there are proofs of this, and certainly in more recent papers of Bruno, in particular the one with the one on pre-Lie algebra deformation theory. But to be honest, I would like to squeeze it into a page and not mention trees, and I haven't been able to do that. So I'm still working on getting the coefficients right. I actually convinced myself 2 days ago that it was false. So I'm totally confused by this point. But I was able to formulate things so I don't actually need that G mu is a morphism. So I haven't included the proof. So the key thing, I'm probably out of time. So can I have a few more minutes or should I stop?
Sure, go for a few more minutes.
Okay. So the thing about L infinity morphisms is that they give a map on Murakatan sets. This is the only reason I'm really interested in them. So just a few minutes ago, well, maybe an hour ago, Bruno asked about the distinction between weak and strong maps of L infinity algebras. There are two different categories. So there's a category of L infinity algebras where we only have linear maps between the underlying complexes. And there's a much more flexible category in which we instead use morphisms of these coalgebras. And I'm going to, for now, mean the much more flexible version. So what we've constructed is one of these very flexible maps from L to M, from the big L infinity algebra to the very small one. And if you have a L infinity morphism of this type, it gives a map of Murakatan sets. So we get a map from the Murakatan locus of L to the Murakatan locus of M. That's, for me, the main result of homological perturbation theory. And it's given by this completely explicit map. And what you see is it also restricts to a map on the Murakatan elements that satisfy the gauge condition. And it turns out that it gives a bijection. So I gave a ridiculous proof of that here. But in fact, as soon as you know that G mu is a section of F mu, that proves it, because G mu, in fact, maps to the Murakatan elements that that satisfy the gauge condition. So in some sense, I think it's the main result of homological perturbation theory for L infinity algebras that the Murakatan elements satisfying the gauge condition are naturally isomorphic to the Murakatan elements of the pushed down L infinite structure by this retraction constructed from homological perturbation theory. That could have been the subject of my talk, but I really like this application. So you see that in particular for comparing Hinich's nerve and my construction gamma, we see that we can reformulate gamma as the Murakatan locus of the chains on the simplices tensored with L, which, although it's not obvious, is seen by the Dupont homotopy to be a simplicial L infinity algebra. That's sort of the, that's written up explicitly in the work of Fiorenza and Manetti, that L infinite structure. So what they didn't observe at that time is that there's a retraction from the Murakatan locus, the hinged nerve of L, to this new simplicial set. And I'm going to use that in the case of Q. So, so here's the main diagram of the talk. We start with gamma of L. We have its inclusion into the Murakatan locus because it's the Murakatan element satisfying the gauge condition. Then we have the map from the Murakatan, the hinged nerve of L to the straightened cubical hinged nerve of L, which is just pullback of differential forms. And then we finally have this retraction that comes from homological perturbation theory. And then it suffices to combine the compatibility with, we have a, you know, basically I'm going to use the Postnikov tower, and then it suffices to prove the isomorphism for the abelian case, and then that's just a standard calculation. That comes down to the fact that the normalized cubical complex of Qn is isomorphic to the normalized complex of the n simplex. And that's the end of the proof. If I could take one more minute, I'll just say that the Deligne 2-groupoid, I'm hopeful that this approach will give a new approach, a more understandable approach to the Deligne 2-groupoid, and that finally it'll be possible to prove that the Deligne 2-groupoid, that its nerve is, so there's a natural simplicial nerve of the Deligne 2-groupoid, and you'd like to prove that that's the construction gamma. And I think it should be possible to show directly that it's gamma Q. That's, I've given some references for that subject. Okay, so sorry to go over. Yep.
Okay, thank you. So maybe a clap. That was very nice. We are out of time. Maybe we can have an informal session of questions if people have questions.